Have you ever wondered how voice, music, or video becomes digital data before transmission? In this video, we'll explore how source encoding works, from analog information all the way to digital encoding and compression. Inside a digital communication system, the source encoder is located right after the input transducer and before the channel encoder. Its role is to convert the original information into an efficient digital format before transmission. To understand how source encoding works, we first need to look at the original type of information we deal with in the real world. Most real-world information is analog, meaning it exists in a continuous form. This means the signal changes smoothly over time without sudden jumps. Examples include human voice, music, and temperature, all of which vary continuously in nature. Analog signals are continuous in both time and amplitude, meaning they exist at every moment and can take any value within a range. Because of this, they need to be converted into digital form before they can be processed by modern communication systems. Sampling is the first step in converting an analog signal into a digital signal. It works by measuring a continuous time signal at regular time intervals. Simply put, instead of tracking the signal continuously, we take snapshots of it at specific moments in time. The basic idea is that an analog signal is continuous, but after sampling, it becomes a set of discrete points. These points form a sequence of values that represent how the signal changes over time. The rate at which we take these samples is called the sampling frequency, or fs. It is measured in hertz, meaning samples per second. For example, 1000 hertzes means we take 1000 samples every second. In general, the higher the sampling frequency, the more accurately we can represent the original signal. A real-world example is CD audio, which uses a sampling rate of 44.1 kHz. That means 44,100 samples per second. This is high enough to reproduce sound smoothly and accurately, making it good enough for human hearing. Quantization is the process that comes after sampling. Before we move on, remember that sampling already converted the signal into discrete time points. Now, we focus on converting the amplitude values of those samples. It converts each sampled value into a finite number of discrete amplitude levels. In simple terms, we round each sample to the nearest allowed digital value. This introduces a small error called quantization noise, which is the difference between the original and the rounded value. This error cannot be completely removed, but it can be reduced. The accuracy of quantization depends on the number of bits used. More bits mean more levels and higher precision, while fewer bits reduce accuracy but save data. After this step, the signal is now fully in a digital form and ready for the next stage, which is encoding into binary bits. Encoding is the final step in converting an analog signal into a digital form. Before we move into this step, remember that after quantization, the signal is already broken into discrete amplitude levels, but it is still not in binary form. After quantization, each sample is still represented as a discrete value. In the encoding stage, these values are converted into binary numbers, consisting of zeros and ones. This creates a digital bit stream that can be easily processed, stored, and transmitted through communication systems. For example, a decimal value like 5 becomes 101 inches binary. Finally, the quantized samples are converted into binary numbers so they can be transmitted digitally. Source encoding also includes compression, which removes unnecessary or repeated information from the digital data. Before we go into this step, remember that after encoding, we already have a full binary representation of the signal. However, this data may still contain a lot of redundancy. The goal is to reduce bandwidth and storage requirements while keeping the important information. This is called redundancy removal. There are two main types of compression. Lossless compression removes redundancy without losing any information, so the original data can be perfectly recovered. Lossy compression removes some data permanently to achieve much smaller file sizes, as used in MP3, JPEG, and MPEG formats. This step makes digital communication much more efficient and completes the source encoding process before the data is passed to the next stage in the communication system. Hope this video helped you understand the key concepts of source encoding and how it works in digital communication systems. Thanks for watching. See you in the next video, and don't forget to like and subscribe.